Hi, this is Eric Riney coming at you again from Webster University with another marketing analytics procedure. In this tutorial, we'll be discussing multi-dimensional scaling. Let's get started. Let's first start with the goals of multi-dimensional scaling. First of all, the goal is to present data in a visual display that will demonstrate the similarities of whatever it is that we're analyzing. So whatever those objects of comparison are, they could be anything from like competitive brands or maybe attributes of your product, and you want to see which ones are most important, or maybe segments within a market and which segments might be more similar to each other, and thus maybe you can combine them together versus seeing segments that are further apart, and maybe you need to have different offerings for each one of those segments. And what we're going to be able to do with this is put it on a two-dimensional scale, or what we call a perceptual map. This is similar to a cluster analysis because you do a data reduction technique, and you're going to combine all of those factors that you're looking at and put them into a geometrical representation of proximity or spacing. And really the difference between MDS and a cluster analysis is that a cluster analysis uses centroids to compare. So you have to pick the number of centroids you want, and then the analysis is going to look at how close each of those factors are in terms of which ones are closest to the centroid, which ones are further away from the centroid. With the MDS, you don't have any kind of centroid as a starting point, so it's more of the analysis doing everything in terms of combining stuff together. And I'll show you exactly what I'm talking about once we get into this. The MDS is a simplified comparison. So it's really just a perceptual map, and it shows you the proximity of the various factors you're looking at. But it's really difficult to interpret the results in a lot of cases because you don't know exactly what the spacing represents. And again, I'll show you what I'm talking about with an example. So first of all, let's look at a cluster analysis versus an MDS in terms of what we'll see in results. So this is a summary of results for a cluster analysis. And with this, what we have are 4 different centroids that were used in this cluster analysis. And you can see here, these were various cities. So I think we started off with 50 cities, and we wanted to see which cities were similar to each other on these various demographic factors. So we have percentage of age, percentage of Hispanic, and so forth. And you can see that the 4 centroids that were pulled out in the analysis were Detroit, Phoenix, El Paso, and Denver. El Paso only has 2 cities as part of its cluster, versus you can see Phoenix has 18. The other thing you see here is that for each of the centroids, you get a really specific description based on each of the factors that was used. So you have a general understanding of the cities that are part of that cluster, right? So we know that the cities that are part of the Detroit cluster tend to have a higher percentage of blacks versus Asians, and vice versa. If you look at, for instance, El Paso, it has a higher percentage of Hispanics compared to blacks and Asians. And so this gives us a really decent way to compare across the centroids or across the clusters and know basically what's making up the cluster. You won't be able to do that necessarily with the MDS. And again, we are using centroids when we do this. Um, so we have an understanding of where the center of the cluster is. All right. This is an example of the specifics of the cluster analysis. So you can see with Detroit, how many of the cities are here and the specifics of each one of the cities. And then we have the overall measure, which is just an average of what we see for each of the demographic variables. You can compare that to the cluster analysis. Now, the one thing you don't necessarily have here is a distance between each of these clusters. And we could do a sum of x minus y squared, a sum of differences, and come up with a measure, but in the analysis itself, we don't necessarily have that spatial distance measured. All right, so let's compare that to what we would have with an MDS. So with an MDS, what would happen is that all of these factors that we use to compare distances are going to be reduced down into XY coordinates. All right, and these XY coordinates are really just spatial coordinates of the distances as a reflection of these different factors that we're looking at. And so there's no way to really tell what the XY coordinate, I mean this 3.53 and this 5.45, what does that mean in terms of percentage of Black, Hispanic, Asian, and so forth? There's no way for us to easily tell that. Now, there are some things that you can do with the perceptual map where you can include these factors, and it gives you a sense of where your different elements are, how close your different elements are to each one of these. But even with that, it's really difficult to interpret. So here's an example of a perceptual map based on the same information that was used in the cluster analysis with the different cities. And what you can see here is that we have various clusters, or what seems to be various clusters, but we don't have any formal clusters that the MDS tells us, oh, this right here is a cluster, and the center of that cluster is, some particular city. Should this be a cluster? I don't know. We can see the proximity of cities to each other. So that's good in terms of representation, but we don't really know which things should be clustered with what. And the other thing we don't really know is what the makeup of the cluster is. So if we attempted to actually create some formal clusters, we could do something like this. And we have, kind of an even size cluster in terms of our circles. It doesn't mean we have the same number of cities, but we do have, equal size clusters in terms of area, at least on this perceptual map. So maybe this cluster over here, San Diego, Long Beach, Fort Worth, and Sacramento is one cluster, and you could compare that to Philly, Chicago, and Memphis. But again, there's no way for us to define what makes up this cluster and how does this cluster differ from this cluster. So if these were brands, it might be really difficult. Let's say, we're this brand down here and we want to move a particular direction. It may be difficult for us just based off of this perceptual map to understand where to move. Now, the simple thing and the power of the perceptual map is that we can easily identify if we're kind of on an island alone, and maybe this is good for us. And in some cases, maybe this is not so good, and maybe we want to be closer to the top brands, right? So maybe we want to be pushed up further. So how do we get there? All right. We could look at a different type of clustering. In this case, we're looking at where we have all of this huge clustering going on and breaking up into smaller formal clusters. And it looks like here trying to put maybe 3 cities into each cluster. This one has 4, but for the most part, you see 2 or 3 cities in a cluster. But this is just a different way that you could interpret this information in terms of what should be clustered together. All right, so those are, the ways that you would look at the output for cluster analysis. So once we get our data together, we'll be able to do something very similar to this. All right, so what is the process for doing an MDS analysis? Well, we're going to do a data reduction again using sum of squared, the difference of sum of squared. And we're going to use that sum of errors squared to look at the rank order of those differences. So if you remember, a sum of errors squared or sum of squared, really it's a sum of squared. I keep saying sum of errors squared, but it's just sum of squared differences. So the sum of squared differences gives you a measure of how similar things are. So the smaller the sum of differences squared is, the more likely those two are similar, right? So then we can rank order each one of those measures from lowest to highest. And that's what we're going to do with our original data. What we're also going to do is create a model. So if you think about it in terms of a lot of the analyses that we do, we have arbitrary models that we use, and then we use solver to try to figure out what the best numbers to really make the model reflect the original data. So in this case, what we're going to do is use XY coordinates, and we'll start with arbitrary numbers, and then we'll have solver try to figure out what those XY coordinates will be in a way that models the original data. All right, so we're going to take those XY coordinates and we're going to do a sum of differences again, and then we're going to rank order those sum of differences, all right, for the XY coordinates. We're going to take those rankings from the original data and those rankings from the XY, and we're going to try to see how similar those two are through fit statistics. So we're going to use fit statistics in order to compare our rank order from our XY with our rank order from our original data set. We'll use solver to change the coordinates such that the sum of differences moves the rank orders around to a place where the rank orders mimic or are very similar to the original data. All right, so that's basically what's going to happen in terms of this analysis. And we have different fit statistics that we can use. We can use R squared, we can use a correlation, or we can use a p-value. Any of those will work, and I'll show you a variety of ways that we can actually do this analysis. All right, so here's an example of model fit. And we have our original rank order data, and this is just arbitrary. This is not something that I actually, went out and calculated some data or anything. But we have these different attributes. So we have 6 attributes we're looking at, and we have attribute 1 ranked all the way to attribute 6 ranked. So you can see how each one of these. And then we have our XY coordinates. And before we do any kind of solver, we see attribute 1 has a ranking of 1, attribute 2 has, so these are in no particular order at the moment. And we can see our R squared is really low. And if you remember, we want our R squared to be high. The higher R squared is, the similar the two things are that we're comparing. So an R squared of 1 means, we have a perfect fit. All right. So after doing our solver analysis, we come up with something like this, where now our R squared is 0.78, much better than it was before. We can see that if we compare the two, our attribute 1 is a 5 in both. Attribute 2 should be a 2. In the original data, it's a 2. In our solver, it's a 1. That's pretty close. It's not exactly the same, but it's close enough. Same thing with attribute 3 and attribute 4. Attribute 5 6 and 6, and attribute 6 is a 3, all right, versus a 4. So we can see that these are pretty close to each other, and maybe if you continue to run solver, you might get something even better, or this might just be the best solution you get. All right, so one of the things, we like to have an R squared that's zero point 0.9 if possible, or, p-values that are extremely low. But in terms of analytics, you get what you get. If that is the best that your analytical tool can do, then that's what you have to use. You have to make a decision whether or not you want to use that or not. All right, so from this point, what we're going to do is actually hop into Excel and begin the process of doing the MDS analysis. So the first thing we want to do is to go through the steps of the process of the multidimensional scaling technique. And this is the case with any analytic tool. The first two steps are the same. One, you want to look at the goal of the analysis. What is it that we're looking for as an output or for information? And does the MDS fit the bill to give us that information? If that's the case, then you continue on. The next thing we want to do is assess and prepare our data for analysis. So you want to go through all the necessary steps to prepare your data by cleaning the data, making sure there's no blanks, making sure it's consistent and formatted correctly, etc. After that, we want to do a checklist of the information that's necessary to do the MDS analysis. So we're going to have our original data, and from that original data, we're going to create a matrix table of distances. So we're going to measure distances similar to what we did in the cluster analysis. And what we want on our diagonals are extremely large numbers, and I'll show you this once we get into the actual data. From that matrix table, we'll develop a second matrix table that is going to rank order these distances that we measured up here. So we'll have two matrix tables based on the original data. We also need to create an XY data set that is going to be our model data. And if you think about it, when we did the regression analysis, we had a trend line that was used to try to model what was actually going on in the data and the relationship between two variables. And that's the same thing here, except in this case, we're going to model using an XY coordinate instead of using a line. Again, we're going to measure the distances between these XY coordinates, and we want extremely large diagonals here. It would be good to have these two extreme diagonals be the same number, but it's not necessary to do that. Then we're going to create a fourth table, and that fourth table is going to be a matrix table of rank orders of this distance model XY data. So we're going to rank order what we created up here in terms of what we measured on our XY coordinates of this data model. All right, and then what we have to do is to come up with some measure of fit, and we're going to try to figure out how well our model data fits our original data, or how well does this model data reflect this original data. And we have a number of different techniques that we can use for measuring fit. We have correlation, we have sum of errors squared, we have R squared, just to name a few. All right. Some other things that we're going to have to do after this checklist. So basically, we're going to kind of run through this checklist right now in terms of getting through this. So the first thing we want to do is make sure our data is standardized. This is kind of a secondary step. Once you've decided you're going to do an MDS, once you've cleaned your data, the next thing is we have to standardize our data to make sure all of our measures are on the same scale. All right. We don't want to have a measure that may be on a 5-point scale and try to combine that with data that has a measure that is looking at $1 million and it's on $1 million scale or something like that. it's just not going to work correctly. The $1 million, that scale is going to hold an inordinate amount of weight in terms of our analysis. So we want to normalize the data so that it's all in the same measure. And you guys are familiar with the z-score, so that's one technique we could use, and that's used if we have interval or ratio level data. You typically don't want to use it if you have ordinal level data, but you will see it used sometimes. We also have this other process of standardizing data, and this is what we use on a ordinal level. So you take your actual score, your variable of measure, you subtract for the whole list of data whatever the minimum score is on this variable, and then we're going to multiply that times whatever the scale we want to standardize to. So let's say this is a 5-point scale. Then our highest scale point would be 5. If this were an 8-point scale, our highest scale point would be 8. We're going to subtract that from 1. We're going to multiply all this together in our numerator. Then we'll divide that by this measure of the maximum number in our actual data minus the minimum number. So even though our highest scale point might, let's say, be 7, maybe it's a 7-point scale, we may not actually have a 7 in our data. Maybe our max is a 5, or maybe it's a 4. That's what we're going to use here. And maybe our minimum is 2. Even though this could be a scale from 1 to 5, our minimum number doesn't necessarily have to be the lowest point on the scale. All right, so we have to find our max and our min. We're going to subtract those, divide those into our denominator, and add 1. And that's how we can create a standardized scale. And once we get into the data, I'll show you how this is actually done. It'll become much clearer once we get in the data. All right, step 5, we have our matrix table. So remember, we have this matrix table up here of the original data, and we're going to have to create a measure of distance. We're going to have to measure the distance between those. And what we're going to use is the sum of x minus y squared. And we've used that previously in several different of our analyses, including the cluster analysis. So we're going to use that same measure of distances to create an overall measure of how far or how unlike or like two different sets of data are from each other. From that, we're going to create a rank order of distances. And then we're going to create an XY table, and we're going to do the same thing. And the same way we do in all of our analytics, we start with arbitrary points on the coordinates, and we're going to let solver actually figure out what the XY coordinates should be. We're going to do a distance matrix table based on this XY coordinates, and then we'll do a rank order from there. Our fit is going to be a comparison of either this rank order of our XY distances to this rank order of our distance measures, or we could do a correlation of these actual distance tables. There's several different techniques that we could use, and I'm going to show you a couple of them. Next, we'll use solver to actually look at these XY coordinates and try to figure out where these coordinates should be. And then we're going to solve for whatever our fit is. So if it's a correlation, of course, we want that to be high. R squared, we want to be high, so we'll maximize those. But if it's sum of error squared, we know we want our error or our differences to be small, so we would want to minimize this. So depending on which one we use for our fit statistic, we'll use that in order to try to figure out what the XY values are. And basically what we're doing is we're saying, where are these XY coordinates that will give us a model that reflects the original data? And that's how we come up with our XY coordinates, which then we can put on a perceptual map. And a perceptual map is just a map of XY coordinates. From there, you can interpret your results and make recommendations. So those are the steps in the MDS analysis. And the next thing we're going to do is to actually get into the data, and I'll show you an example of how to do this. All right, so let's take a look at this first example. So let me just read through it real quick, and then I'm going to actually show you how I've gone through it, and then we'll go back and actually go through it. So the following data are a list of average ratings of 6 competing brands on their 5 most important attributes. 9 represents highest important value. For instance, attribute 1, which is ATT.1, and attribute 2, ATT.2, are least important for brand A, so that's why they have a score of 1, while attribute 3 is most important, and actually on this one, attribute 4 gets a higher rating for A than any of the other attributes. Attribute 5 was measured using a 5-point scale instead of a 9-point scale, so you can see here that this only goes up to 5. These actually go up to 9 on them. And this could happen from time to time where research is done and for whatever reason there's one question that's asked on a 5-point scale, and there's other ones that are asked on a 7-point scale, and there's some that are asked on a 9-point scale, for whatever reason that is. Now, just because this only goes up to 5, that does not necessarily mean this is only a 5-point scale. So you want to be careful that you don't look at your data and just assume, well, since there's no 9s in this one, it only goes up to whatever the highest number is. That just could mean that nobody scored it a 9. So for instance here, the highest number is 8. So you could make the mistake that this attribute is on an 8-point scale. Well, in fact, it is on a 9-point scale. It's just that no one actually rated it on a 9-point scale. All right, so one of the first things we're going to have to do, the data is pretty clean here. We don't have any blanks. We don't have any, this doesn't say 4 in here instead of it actually being a number or anything like that. So we don't really have to worry about cleaning this data, but we do need to standardize this data so that all of these are on the same scale. All right, so we could use a z-score, or we could use the other standardized technique that I showed, and that's one of the things I'll show you. But first, let's hop over to the actual place where I went through the entire analysis just to give you a bird's eye view of what we're going to be doing, and then we'll go back and actually do it. So here's our original data right here. I've calculated a mean score and a standard deviation for each one of these measures, and I've actually here created a standardized score using that technique that I talked about over here in the steps for standardizing a scale. And you can see here, since we're doing a 9-point scale, it would be the score value, which here would be a 4, minus the minimum. The minimum on this scale is 1, times 9 minus 1, which is just 8. All right. And then maximum, so the maximum on this scale is a 5, minus the minimum, which is 1, plus 1. So that's what I've done here. It looks really fancy here the way I've done it, because if you look up here in terms of this formula, I have J8, which is the score, right? So 4 is my score, minus the minimum. So I'm taking this formula of minimum right here, and I'm saying give me the minimum out of my data set. And it's good to use this minimum value because if you have a large data set, it may be difficult for you to find the minimum value, especially if it's not on a particularly small scale. So using this minimum value, or perhaps doing descriptive statistics and coming up with the minimum score will give you this. It's better than trying to eyeball it. And I did the same thing over here on the maximum. It's the same exact thing where I'm saying search for the maximum value and pull it in. All right, so we have our score minus our minimum times 8. Remember, it's just whatever our maximum scale number is minus 1. So in this case, it's 9 minus 1. So 8. Then we're dividing that times the maximum value minus the minimum value. So 5 minus 1. I'm just using formulas there, plus the 1. And so that gives us now a standardized 9-point scale of 7. So on a 9-point scale, a 4 is a 7. So what a 4 is on a 5-point scale, it's a 9, it's a 7 on a 9-point scale. A 1 is still a 1. A 5 is a 9, right, which makes sense. A 3 is a 5, and so forth. So that's kind of how you interpret this. Now, the other approach we could take is we could actually standardize using the z-score all of our values over here. And if we look at this formula, all I did is use the standardize formula, which is equal standardize. And then it asks for our various measures. So the first one it asks for is what is the score? And that's this value. And then it asks for the mean. And then it asks for the standard deviation. So that's what I'm pulling in here. And then I've just copied this formula across and down. And so now we have a standardized matrix table. Now, one of the things that you can do to just make sure it's done correctly, on a standardized scale, you have a mean of 0 and a standard deviation of 1. So that just means this was done correctly. All right, so if you remember the next step in the process, after we've standardized our scale, then we have to create a distance matrix, and then we're going to rank order those distances. So if we come back over here, the next thing we're going to do, and this right here, I've just copied this data down here and just, I'm using this measure instead of the original data. So this is my new data set, which includes the standardized attribute number 5. All right, so we're going to now have to create a measure of distance. All right, and what we want here, you need to think about what it is you want on your perceptual map. So here what I want on my perceptual map is an understanding of how brand A, B, C, D, E, and F relate to each other. Not relate to each other, but how closely they're associated with each other, right? So what's the distance between these? In some cases, you might want to do attributes. Maybe you want to know how similar two attributes are to each other. So if that's the case, instead of doing this matrix where we're doing A's, or we're doing the brands, we could be doing the attributes. But in this case, we're doing brands. Okay, so as I mentioned, along this diagonal, we want an extremely large number. I tend to use 100,000 because in most cases, that's going to be much larger than any of my measures of distances. So how do we measure distances? If you remember correctly, the sum, and let me just write it over here so we can see it, equals sum right here. This sum x minus y squared is what we're going to use. All right. And let's just do this. If you remember correctly, what we're doing is we're taking the sum of one set minus the sum of a second set, squaring that to get rid of any negatives, and using that as an overall measure. So for instance, for this A, and the reason on this diagonal, we want this diagonal because this is a combination, this is a comparison of A to A. There is no difference between A and A, so this is going to be 0. And when we get down here to our ranks, we don't want the diagonal to be our lowest ranking, and it would be if these are all zeros. if we're doing rank order, right? So we want this to actually be the largest number. That's why we're just going to put in there a really large number. But let's look at this brand B to brand A. Basically what we're doing, and you can see here, if we look at what's highlighted, we're taking the sum of differences between attribute 1, so 1 minus 6 squared plus 1 minus 7 squared plus 7 minus 4 squared plus 8 minus 2 squared plus 7 minus 1 squared. So we're going to take the difference of these squares, and that gives us the sum of square differences between these two. And so that comes out to be 142. All right. And you see it's BA here. It's the same thing here. AB is 142. So you'll have the same thing if you look at this like as a mirror. You'll have the same thing on top of the mirror as you do on the bottom, or maybe a lake or something like that. All right, so here we have a comparison of C to A, and if you look what I have here, that's exactly what I've done, A and C. All right, so let me explain my actual formula in here so you can see what I've done. I'm saying if E26, which is this right here, equals F25, which is this right here, so if these two are equal, I want this large number, this 100,000. So that will take care of my diagonals. If not, then what I want you to do is sum my A values and my, well, in this case, it's the A and A values, right? So let's look at this next one right here. So if these two are not the same, which in this case they're not, then sum this 18 row, so F18 through J18, and this F19 row, which is the B values. And that's what I've done. All right, so it gives me the measure. If we go to the next one, you'll see it's the same thing except the B has jumped down to C. If we go to the next one, you have the same thing. All right, and again, once we get in, I'll show you how it's actually how to actually type that in. All right, so this gives us our distances between each one of these brands. And like I said, you could do this for attributes. If we did it for attributes, instead of doing rows, we would actually do columns. So you would have the difference between attribute 1 and attribute 2, the difference between attribute 1 and attribute 3, and on the diagonals, because this would be attribute 1 and attribute 1, you would still have 100,000. All right. So the next thing we're going to do from this is we have to create a rank order. So we want to order the ranking. We want to rank each one of these from 1 to the highest number for this whole table. All right, and that's what I've done here is rank, and if you look here, it says rank this first one. So I want this cell to reflect this one. Rank this cell amongst this entire table, and I've named this table original data. So amongst this table, and we want to go, 1 means we want to go from 1 up to the highest. All right, so apparently we have a ranking of 31. 31 is our highest, and that's on the diagonal. You can see here it's on the diagonal. Here, if you look at this one, this has moved down to BA, that cell, BA, and rank this amongst all of these, and this 142 has a ranking of 29th position. All right, so if we go over here, we can see that this distance between C and E seems to be the shortest distance because it has a rank of 1. All right, and the next one, D and E, seems to be pretty close too amongst all the other rankings. So now we have a rank order of these distances. And remember, these distances are a measure of the differences of our original data. All right. So a way to think about this is that this data measures the distance of each one of these brands based on these 5 attributes. And now what we're doing is we're ranking these distances from lowest to highest. All right, the next thing we're going to do, if we go back over here to our steps, is that we have to create an XY table, and we just start with arbitrary points. So I would just create this table, and what we want this table to be is our factors, our variables that we're using. So A through F, in this case, these are our brands, A through F, and we want an XY coordinate for each one of these. And the way this would start off is I would just have like 1 all the way down, or 0, or who knows, I may just put 1, 2, 3, 4, 5, and so forth. And that's how I would start off with my arbitrary coordinates. I've actually already gone through the solver, and this is the answer. So I'm going to leave this as is for now. But now what I'm going to do is I need to take, again, my differences, a measure of differences on these XY coordinates. So similar to what I did above here, when I took my differences between XY based on these 5, what I'm going to do here is take the difference of, I'm sorry about that. I'm going to take the difference of this A on XY and B on XY, and then I'll take the difference of A and C. So if we look at this here, it's the same thing, where it's going to be a high number on the axes, or I'm sorry, on the parallel, or you know what I'm trying to say. I'm losing my thoughts here, sorry. But if we go here, you can see this is comparing the XY of A and the XY of B. Here, this is comparing the XY of A and the XY of C. Now I have, again, a sum of differences between these XY on AB. And the last step is that I'm going to create a rank order again. And because this matrix table is the same size as the matrix table above, I'm going to have the same number of rankings. So I have from 1 to 31 in terms of different ranks that I could position these in. So from 1 to 31, now the rankings are standardized because they're both 1 to 31, which is different than my measures here. My measures here are not necessarily going to be the same as these measures up here. So it would be hard for me to compare my sum of differences to each other. But my rank order, I can compare to each other because they're on the same measure. And that's exactly what we're going to do. We're going to try to fit our original rank order data to our model rank order data. And there's multiple ways we could do this. We could do a correlation between the two, which is what I've done here, correlation, or we could do an R squared as well. And R squared would simply be where we do equals R SQ, and we would take our original rank and we would do our model rank. All right, and then we have our R squared. All right, so we can do it either way. And what we're going to do then is to use solver to figure out what XY coordinates each one of these brands should be in order to match the rank order up here to this rank order. All right, so this is going to go through the calculation of distances, and then that's going to translate into this rank order. And if this rank order matches this rank order, then we have something that's pretty reflective of the original data. And so now we've transformed our attributes and brand data into this XY coordinate. And now we can take that XY coordinate and actually put it on put it in a matrix table, and we could see where our distances are from each other. So you see here, it looks like A and F are actually pretty close together. D, C, E are pretty close together, and B is over here on its own. And as I mentioned before, it's kind of hard to really establish, if these are a cluster, what cluster is this? What are they high on? What are they low on? What is this cluster? If we were brand B and we wanted to move over this way, what does that actually mean? What would we have to increase or decrease? Or, if we're brand A and we want to, or basically brand maybe C or E, and we wanted to go to some blue ocean, what does that actually mean for us to move from here to here? Which one of these attributes do we need to make sure we're, doing a better job of instilling that it's important, it's part of our brand? So those are some of the things that are kind of difficult to interpret in terms of how you might actually use this data. It is very good, though, in terms of virtually or perceptually looking at distances, right? And we can actually measure these distances. We actually have the distance between these, and we can measure that. And that's something we don't have in the cluster analysis, is the actual distances between our elements. But we do have that here. All right, so that's kind of an overview of what we're looking to do. I know it looks like it's a lot, but hopefully it makes sense what we're trying to do. And once you think about it and you can think intuitively about it, then it should make it easier not only to understand it, but to actually do it. So the next thing we're going to do now is actually go in and recreate this. All right, so let's go all the way through the process and see what we can do. All right, so here's our original data. Again, we want to make sure that we know we're going to be doing a multi-dimensional scaling. And this one we know, of course, that's what we're doing. The next thing is we want to make sure our data looks good, and generally speaking, there's no issues with the data. The next thing we want to do is think about all of the things that we want or need, all of the elements that we need to do this analysis. So we're going to have a measure of distances. We're going to have rank order of that original data, rank of distances. We're going to need XY values. And then we're going to have distances measured from that. And then we're also going to have rank order of those XY distances. So just keep in mind the things that you need to accomplish. All right, the next thing is that we need to make sure that our data is standardized. We know that these first ones are standardized, this first four, but this one is not on the same scale as the rest of them, so it's not on a standard scale, and that's what we need to do. Since these are all on a 9-point scale, I'm just going to transfer this into a 9-point scale. And if you remember correctly, to do that, let's just copy this over from here. Where is it? Right here. Just so you know what we're going to be doing here. I guess I could have copied it from there. All right, and we know this is going to be a 9-point scale. So I like to do this just so I know exactly what I'm doing. And I'm going to turn this right here to 9-point because I know this is going to be 9. Or I could just put 8 in there if I wanted to. All right, so this is what we have to transform this 5-point scale into. And I'm just going to do that real quick right here and show you how I did it. STD. All right, so equals, and we know we have two openings here, our score, this is our original score, minus, and then we want to use the min. I mean, we know 1 is the minimum. If you want to put 1 in there, you can, but I'm just going to use the min function. And I want to do this whole set of data. You know, if this data went all the way down to 1,000,000 folk, I want to use the entire data to identify the min. And I want to lock that in place. So I'm just going to put my $ in front of both my row value as well as my column values to lock that in place because I don't want that to move. All right, so there we have it, our score minus our min. I'm going to close that off. We want to multiply that times, and I could just put 8 in here. I could put 9 minus 1. I'm just going to put 8 in here since, you know, I know what it is. All right, close off the brackets there. And then we want, this is our numerator, and we're going to divide that by our denominator, which is our max. And again, I'm just going to do this. And instead of typing this in, if you want to use, on some keyboards, you have your quick function keys that you could use. So like on a lot of your PCs, you could use the F4 to toggle between the different versions of locking these formulas in place, these cells in place. All right, so that's our max, and then I'm going to subtract that from the min, which I have here. I'm just going to copy this real quick. I could type it in again, but I'm just going to actually just copy that, close off, plus 1, close off, and there we have it. And it says 4.8. We're going to round this off. It's better to have whole numbers than, you know, these in-between numbers. And, you know, something here does not look right because in my original data, if I'm not mistaken, that was a 7. Let me go over here and look real quick. Yeah, that was a 7. Uh-oh, what did I do? So let's go in here right quick and take a look at this and see. Sometimes you have to, our J8 minus our min times 8, our max minus our min plus 1. Oh, I put the parentheses. That's what I did. So before I put the parentheses, if I can go back, you see here I actually close this off, and the 1 should be on the outside. So that's what I did. All right. Oh, let's go back. There we go. All right. And just because my OCD, I like to have this centered, and I'm going to copy this all the way down, and there we have it. So now I have my standardized scale on a 9-point scale. I've transformed this 5-point scale into a 9-point scale. All right, I'm going to now create my matrix table, and my matrix table is going to be based off of brand. And like I said, we could do it off of attributes, but I'm going to do it based off of brand. So I'm going to copy this and you know, recopy the information. Actually, let's just copy this whole thing. Oh, sorry. Because I need to make sure that I include the right attribute score. So let's just copy this down and just copy this over here as well. And you could do the equals. Uh-oh. Not sure what just happened there. Let's try. Sorry guys, my computer is moving. It's responding really slow, And so I'm hitting things multiple times, and I really should not be hitting things multiple times. All right, so let's just do it this way. I'm just going to do equals this and call it a day, because I know that's going to work, right? And there we go. All right, so now what I want to do is create a matrix table just on my brand, right? Because that's what we're looking at, brand, and not at attribute, right? We want a matrix table on that. And you really could, if you wanted to, you could do it on both attributes. You could create one large matrix table that has both a comparison of A and B and attribute. I've seen that done, though I don't think it's really that helpful to do it. So I'm just copying the brand here, and then I'm going to copy it across here by doing a special copy where I'm flipping or transposing. And now I have it both across and down. Let's underline that. All right. And if you remember correctly, what we want to do is we want to do a measure of these differences. Now, if you have a large amount of scale of elements that you're using, you might want to go ahead and label all of your data. So if this, let's say there's maybe 50 or 25 on this brand A, I might highlight this and go ahead and just label this brand A and label this brand B. It'll just make it that much easier to actually, when you're down here trying to put things in a matrix table, especially if you have a large matrix table. All right, so if you remember correctly, what we want to do is say if this equals this, then we want a large number. So if this, and I want this to go down, but I don't want it to go across as I move over. So I want to lock in place my row, but not my, my column, but not my row. So I want to lock in place my E. So I want to keep it in this column E, but I want to go from row to row. All right. And so if E24 equals this F23, and in this case I want to lock my row in place because I wanted this to shift over for each column, but I don't want it to shift down. So if those two are equal to each other, what do I want to happen? Comma, I want 100,000. If not, I want to do my sum x my, so sum x minus y squared, right? And okay, well, it's going to ask me what's your x array. My x array is going to be A, and my y array, I'm going to hit comma, my y array in this case is also going to be A. All right, and we want to keep this in place as well, but only in terms of shifting over columns. We don't want this to shift over columns. We don't mind it shifting down, but I don't want it to shift over columns. All right, so I'm going to lock this in place, all of my columns. All right, so there we have it. If I copy this across, let's see what happens. So one of the things we're going to have to do here is we want now this to compare A to B, right? And all I did was I just dragged one of these down. So one is A, one is B, all right? And then I want this one to compare A to C, and I want this one to compare A to D. And again, if I use brand A, brand B, brand C, this would work a lot quicker, maybe. I mean, certainly if you had a larger data set, it would work a lot quicker. All right, so there we have it. So now we have, and if you want to, because I'm sure there's some decimal places. Oh, no, maybe not. All right, and I'm going to center these as well. All right, so let's copy this down and see what happens. All right, so first of all, my diagonal is working really well here, so that's good. But these other things don't seem to be working so well. So what's going on here? I need to pull this up to A. So one has to be A, one has to be B, 142, 142. There we go. On this one needs to be A again. So I'm just pulling that up here. Got to pull this back up here. I'm going to pull this back up. And here. Same thing, I'm going to pull this back up. All right. On this one, looks like it did not quite shift correctly, so we want B and C here. All right, here we want B and D, correct? And one of the things you could check to make sure is that on your diagonals, these should be the same. 142, 142, 78, 78, 74, 74, right? I'm not sure about this CB. CB here should be 90, but it's not. And that's because I'm looking at BC here. Okay, and I'm looking at BC here. What's going on? Oh, this one is not correct. That should be BC. There we go. So that's one of the ways that you could check to see if, things are being done correctly. So this should be C and D. Just dragging that up. And this one should be C and E. And this one, is because it went all the way down, should be C. This one's off the chart. That's why we're getting that error term there. And F. All right. Thinking if I copy this across, it may actually work. Let's see. Let's see what happens here. D and E. So we need D here. And here we need E and F. Just drag this down there to F. F and B. And then this one should be F and C. And this one should be... Now, in your textbook, it takes you through using the index function and offset functions, which, you could use. Actually, they work a lot faster once you set them up, but setting them up can be a little bit tricky. And so I didn't want to really get into, trying to show you how to set up the index function or the offset function. But I mean, if you want to try to use those, they really do come in handy in terms of being able to get through this relatively quickly, especially once you initially set them up. And to use those, basically what they've done is they've put 1, 2, 3, 4, 5 all the way down, and then 1, 2, 3, 4, 5 across, and they use those to help index where you should find the data. All right, so D and F. Looks like we have one more here. It still doesn't look right. I'm going to pause real quick just to make sure I have this set up correctly, then I'll come back. Okay, so I've gone through and just made sure everything was correct, and now it's correct. So once I have this set up, the next thing I want to do And you could label this if you want to. It may help when you're doing your rank order. So I'm just going to highlight my actual data, and I'm going to call this old data for original data. All right. And I'm going to copy this entire thing down. And, uh-oh. Yeah. Let's go ahead and just delete this right quick. And now equals rank. I'm using the rank order. And I want to rank this cell, so whatever the contents of this cell, and my old data, right, which is this entire data, comma, and do I want it descending or ascending? I want ascending, so I'm using 1, close, and now it puts in 31. If I copy this across and then copy this down, now we could see, you could verify our smallest number is this EC, and it's 1. Same thing here. EC is 1, 5. So looks like we're doing well there. All right. So the next thing we need to do now is that we need to create an XY coordinate of our brand. So I'm just going to copy my actual elements. Let's copy them down real quick and create this X and Y. Make that bold, underline. And we're just going to have arbitrary values in here right now. 6. And I'll go the opposite. 6, 5, 4, 3, 2, 1. Make sure all these are... All right. So now I need to create a matrix based on these, and I'm doing the exact same thing I did here in terms of my matrix, except it's going to be the sum of differences for this instead of what I used up there. All right, so I'm just copying this down real quick. I'm going to drag this down here. And I am going to just drag this over. We're going to do it this way. I'm just seeing if this works. I don't know if this will work or not. I'm just trying something while I'm recording, right? So put this here and close it. And then these two are like that. All right, so let's see what happens if we go across here. So this, this will become this. Yeah. All right, so I'm going to pause and I'm going to do this real quick. It's the exact same thing, so you should pretty much understand what I'm doing here. I'm just going to pause real quick and finish this. Okay, so I finished this up, and if I just click on one of these, you can see, this is... oh, wait a minute. Did I not do that right? Uh-oh. I think this is off a little bit. This should be A and B and not. All right, let me pause and make sure I have this done correctly, and I'll be right back. All right, so I've fixed my errors, and I believe everything looks good now. So for instance, here we have a comparison of A and B on these X and Y coordinates, and the difference between the X and Y coordinates for A and B, which is 2, and you see the same thing here. And for A and C, we have the difference between the X and Y coordinates, and it looks like it's set up correctly there, and that's 8, and this is 8 as well. And you see, so looks like everything is set up correctly. Okay, so now that we have our XY coordinates and we have our matrix that's measuring the difference between our XY coordinates, the next thing we want to do is we want to rank these. So let me go on and label this really quickly, and we'll call this model data, mod data. All right, and I'm going to copy this whole thing, just how I have the shell. And let's just delete all this right quick. And here we're going to say equals rank. We want to rank this cell amongst our mod data, which is that whole set of data. We want to do this in ascending. All right, and it should be 31, which it is. We'll carry this across, and then we'll carry this down. Oh, went a little too far there. All right, so now we have our rank order for our x-coordinate distances. Here are x-coordinates. Our x-coordinates feed into our distances measures. Then our distances measure feeds into our rank order of these xy coordinates. And then above we have our ranking of our original data distances, and these distances are a measure of our original ranks. So now what we want to do is we want this to be as close to this as possible. So we want solver to solve for these in such a way that it creates something where this matches this rank order. All right. So we're going to let solver do that for us. One of the things I want to do really quickly before I do that is I'm going to go on and show you how to actually set up a perceptual map. That way you can see how the perceptual maps looks before and after solver gets done. So really quickly, there's a couple ways to set up a perceptual map. We're going to do insert, and for the time being, instead of, I like to do these bubbles, but for this one, instead of doing the bubbles, I'm just going to do just dots for now. All right. And we can set it up this way, and we have a very easy, looking line, and it's simply because I did 1, 2, 3, 4, 5, 6, and then 6, 5, 4, 3, 2, 1. So it's very straightforward looking. And if you want to add in labels, unfortunately Excel does not have a great way for you to add in labels. So if you want to add in labels right here, you would actually have to click each of your data points, right mouse click, add label, and it's going to add the y variable, because right now it's saying that that's what this is a measure of, this y. But really we want to change that. So you would double click on it and then just go ahead and change this, and close this, change this into whatever this one is. So this one is coordinate 1, 6, which would be A. Come on. Let's do a little bit. There we go. And if you wanted to, you could put brand A in there or something like that. So now as this moves, this A is going to move with it, and I'm actually going to, I like having my labels in these circumstances over the data points. So I'm going to do above, all right? And then you would actually have to do this for each one. So if I'm going to do one more, add label, and it's going to be our Y for now, but I'm going to change this to make that a little bit bigger just so I can get in there. A B for my B data point, and I want this to be above. All right, so again, I'm going to pause the video real quick and just finish doing each one of these, and then I'll come back. All right, so I've finished putting in my labels. The other thing I like to do is to take out these grid lines, because usually in a perceptual map, you only have your X, Y axes. You don't usually have all of your grid lines. So I'm going to format the grid lines in no lines. And let's do the same one for these horizontal, no lines. And so now we have as our y-axis and our x-axis. And usually when you have a perceptual map, your x-y axis will be more of a cross instead of this L-shaped. But what we're going to do in solving this, right now I only have positive numbers, and that's why you only have one quadrant of what could be an XY. So if you extended this down and you extended this over to negative numbers, this would only be one quadrant. There would be 4 other quadrants. So when I do solver, what I'm going to do is I'm going to solve for a range, usually from -3 to +3, -5 to +5, and so forth. So you'll see how this will actually change, but I like having this set up first just to kind of eyeball it as I'm looking at data. And you could change this label to, you know, like brand perceptual map or something like that. Okay, so we have basically everything set up. There's only one more thing that we need, and that's our fit statistic. And I'm going to do a correlation first. And we'll set it up here, equals correl for correlation. All right, so what 2 data arrays do we want to correlate? Well, we want to correlate, and if I had labeled this, then I could just type that in, but I didn't label this. Sometimes I'll actually label my rank order data as well, but I didn't do that this time, so I'm just going to highlight it. So we're going to do that for the first array, and then the second array is going to be our XY. And if you look at our correlation right now is 0.36, and we of course want this as high as possible. The higher it is, the closer to 1 it is, the more correlated the 2 are. If it's 1, that means these 2 are exactly the same. So I mean, that's what we're shooting for. If these 2 are exactly the same, then that means these XY coordinates are a true reflection of what's going on in this data up here. All right, so we're going to go into solver, and we are going to maximize correlation in this circumstance by changing what? We're going to change these numbers here, our XY coordinates for each one of our brands. We're going to add in some constraints. So one constraint is that I want these XY coordinates to be less than or equal to, and let's do a range of -3 to 3 right now. And we'll change this, and I can show you how it looks when we change it, because sometimes just by changing the range of possible coordinates, you can actually increase your correlation or your fit statistics. And sometimes by reducing the range, you can do that as well. And also in terms of reflecting the proximity of the brands, that can be impacted by your range. So we're going to say greater than or equal to -3. So our range is going to be from +3 to -3. And I'm going to hit OK. I want these to, I don't care if they're negative, they don't have to only be positive, of course not, because I have a range of -3 to 3 here. We're going to use evolutionary solver for this, and we're going to run it and see what happens. And depending on how big your data set is, this could take a minute or two, or it may take up to, 10, 15 minutes. Just depends on how big your data is. All right, looks like our solver found a solution. It can't improve on the current solution. And we see what our coordinates are that it's come up with. Our correlation is 0.98, so 0.99 actually, so that's pretty darn close. And if we compare these, we see that 31, 29, 11, 31, 29, 13 instead of 11. This 9, 20 here instead of 19, 7. So you can see it's pretty close, which means these rank orders, which are a reflection of our distances, then are pretty close to each other, which means that our coordinates reflect what this data is saying up here. So we've literally transformed this data now into a coordinates type of XY, so a two-dimensional data plot. And you see here the relationship that we have in terms of the data. So here we can see that E and C are highly related brands, and D is relatively related as well. A is kind of on its own, but it's in close proximity to E. And B is all alone over here. And really, if we were to change these axes in terms of the ranges, so here I'm actually going to go from -3 to +3. And let's change this axis as well. Let's close that and try this again. Let's try that one more time. There we go. Format axes, and we're going to change this to 3. And really what happens is that, Excel just tries its best to create a plot that looks like something that, would be useful to you. So here, it doesn't really change anything in terms of what we see. We see that A and F are relatively close. E, C, and D. We see the proximity of those, and B is over here. And as was mentioned, there's really no way for us to tell what this means. We know that these brands are relatively closer in terms of the perceptions based on these attributes that we looked at. So the attributes that we're using, the perceptions of those attributes are more closely aligned between these 3 brands than certainly B and F and A are pretty close to each other. We can at least measure the distance between C and E. We can go over here back to our original data, and our measurement of distance between C and E is 7, right? Versus our measure of E and D is, let's find D and E is 9, right? So, these are pretty close to each other, but we see that D and B is a lot further, and E and B is even further, right? And I'm sure C and B is pretty far too, all right? So there you have it. That's how you would do an MDS. When you do a write-up on this, you would say a data analysis was, MDS data analysis was conducted on data, which you could say something like data from a marketing research study regarding brands and attitudes, or I'm sorry, in terms of looking at the importance of attributes and brands. The perceptual map indicates that E, C, and D are relatively close, with E and C being the brands that are most like each other on the 5 attributes, while B is on its own and A and F are relative brands. You could also say something like further analysis would be necessary in order to determine the makeup of this cluster versus other clusters. All right, but there you have it. That's a simple perceptual map based on an MDS analysis. All right, so one other thing I want to show you, well, 2 other things I want to show you real quick. One, these cluster cities, if we did the cluster analysis, and if you look at this cluster city, I mean, if we did all 48 of these, that's a lot of information. So we already have our z-scores when we did the cluster analysis, and I've just copied that data over. So we have our standardized data. I've gone ahead and done this for each of the cities. So you can see down here I have all of the distances measured, and the way I did this, I'm going to click on here right quick, is I actually labeled. So we have Albuquerque Z data and Baltimore Z data right here, and so I've done that for each one. And if I click on here and go up here, you could see that this is Albuquerque and this is Baltimore. And that's what I've done for each one of these, and I'm just going to escape out of there. And then I did my rankings for this information. Then I did my my XY coordinates for each of the cities, which are over here. And then I did a distance on those, and that's right here. So if we click here, that's my rank. If we click here, if we click here, then we can see, and here I actually did use the offset just because with this amount of data is so much easier than trying to do this with highlighting. So I'm using an offset for the XY coordinates. All right, and that's my distances for my XY, and then I do my rankings on my XY coordinates. And we come up here, this one I'm using R squared. You could use R squared, you could use correlation, but in this case I use R squared, and I might try to go back and do a correlation just to see what the difference is. And this is how I came up with the data that I referred to earlier when I was lecturing on the MDS. And again, I mean, we could create clusters, but it's really hard to know exactly what these clusters mean. And if you were to compare this to our cluster analysis, this really looks totally different than the cluster analysis. I've been trying to do different things in order to see how I could get the MDS analysis to present something that's closer to what we find in the cluster analysis. It hasn't worked yet, but I'm sure, once I figure it out, tweak it, then I could get something pretty darn close to what I have in terms of results of the cluster analysis. But there you have it. That's the MDS. So there's only one more thing I'm going to show you, and that's how to do your perceptual map if you want to have different size bubbles on your perceptual map. All right, so in this next example, we have data that's a breakdown of brand market share by segment, and the segments are done by age categories, and the total market size is 12 million, with 10%, 30%, 40%, and 20% representing the various age groups respectively. So 10% of this 12 million is this um, less than 20 segment, and that is represented across these brands as 14% and so forth. And the same thing for each one of these. Now, one of the things you want to be really careful of when you're looking at data like this is that what is this a percent of? Is this a percent across the brand, or is this a percent across the category for, this less than 20? So if we were to do a sum here, this should add up to 1 or 100%, and it does. So this breakdown is a percent of the total less than 20. If this didn't add up to 1 or 100, then if you were to possibly go across this way, it may add up to 100%. And that means that these percents would be a breakdown of percent of brand A. So the total market share of brand A would be however much it is, and then that would be represented by each one of these segments. So that 100%, let's say this, if we were looking at this going across, and let's say A has, I don't know, 100,000 customers, or whatever percent that is of the market, and then they might have 10% of that market share that A has might be less than 20, and then another 30% and so forth. So that would be a look at the breakdown of the share of A's market by categories. I hope that makes sense. So, you just want to be really careful when you're looking at percentages that you're looking at these the correct way. All right. So I'm not going to show you, I've already gone through the entire analysis, so I'm just going to show you how this analysis plays out. Again, here we know we're doing a multi-dimensional scaling analysis, so we don't have to worry about that. Check off box, or check one in the step. The next step, the data is beautiful. It's all in percents. Check that off. We know the various things that we need to do, so check that off. We want to make sure our data is standardized. It's already in percent form, so it's standardized. It's between 0% and 100%, right? So check that off. Now, if this were something else, like you could actually go over 100% depending on what it is. You can't in this one because these are specific categories of segments, and it only goes up to 100%. You can't have more than 100%. So we don't have to worry about standardizing this in any kind of way. I've gone ahead and done my sum of differences. So here, sum of A and B. And then I've created my rank order table based off of that. I did my XY coordinates. I did my sum of differences of that, and then I did my rank order from that. And here I'm actually doing a correlation of my two rank order tables, and you can see that we actually have a perfect correlation of 1. And we see what that looks like over here. So we have brand C and B, which are relatively close together. Brand D seems to be on its own for the most part, and brand A is on its own for the most part. And so, maybe if brand A is the leading brand, and brand D may be a follower brand, and they're trying to follow the the lead of A, then they may want to move themselves closer to A so they can do a me too. We're just like A, right? And that's okay. I mean, a lot of times we automatically think that you have to have a uniqueness about your brand, which you do, but you also want to have some things that are just like the leader, right? We're just as good as the leader, but this is how we're different, right? So if brand D was trying to do that, it may not be working too well, at least in terms of this. Now, this perceptual map is not one based off of perceptions of individuals. This is just, age categories. And again, it's kind of hard to determine what this means, right? How much of the market does C and B have? I mean, you could look up here and kind of interpret this maybe, but it's really hard to do, right? To see what that actually means, other than B and C seem to be going after the same market segments of age, and D seems to be going after its own segment on age, and A seems to be going after its own segment. So that is how you would do it with a correlation. I've also done it here in terms of looking at the sum of errors squared, right? And the sum of errors squared is a little bit different, because with the sum of errors squared, what we're doing here is we have our sum of differences, the way we normally do, for each one. And what we want to do now is look at the difference between the sum of differences, right? And all I'm doing here is I'm taking the square root of kind of the sum of differences of the sum of differences. So I'm looking at this minus this squared, and then taking the square root of that. And that's what I'm doing for each one of these, right? So basically I'm saying that this difference and this difference need to look alike, all right? So I want this AB to look like this AB, and so forth, all right? And I'm still doing my coordinates the same way, but instead of doing my ranks and comparing ranks, now I'm doing the sum of errors, and I'm looking at the, how close are these sum of difference measures based on this down here. And you again would run your solver on your XY, and you would do a minimization. So we want to minimize, in terms of this one, minimize our sum of errors term. And in this one I did -2 to 2 instead of -3 to 3. And so now we have a map that looks like this. So we have A and D a little bit closer together here. B and C are still relatively close. So it looks a little bit different than the other one here. So depending on which one you want to use, which one you think best represents your data, or maybe you can best explain it, maybe that's the one you want to use. All right. So the only other thing that I want to show you, and I thought I had it here, but it does not look like I do, is actually how to do one where it's a bubble, and so we can look at the size of the bubble, and that will indicate how big of a market share each brand has. All right, so we had this original information in terms of the total market size of 12 million, and then how much each one of these groups has of that 12 million. And we can actually calculate the share of each of the brand's segments, all right? And then the overall percent for each brand. So what I've done here is I've taken this 14%, which is A's share or percent. A has 14% of this less than 20 segment. And this less than 20 segment represents 10% of the market. So if we multiply this 14% times 10%, which is less than 20 age segments share of the entire market, this 12 million, that gives us 1.4%. So A has 1.4% of the market, which is represented by this less than 20 segment. All right, and we do that for each one. And if we add all these up for A, then that gives us the overall market share for A, which is 29%. And the overall market share for B is 24%, and so forth. All right, so that's what we can then use. And it looks like I have something different here. Why is this different? Not sure what happened here. So this should equal this, right? And let's go all the way down, make sure we've done that correctly. Uh-oh, 24, 22, still didn't, there we go. All right, so we see what the percentage is for each one of, now this is not necessarily going to be part of our data. I don't know why I put it next to it. Not sure. But I am going to use it down here for my perceptual map. So really quickly, I am going to get rid of this perceptual map and start completely over because I'm going to use a different perceptual map to do this one. So I'm going to do insert, and in this one, before we use just the dots, but in this one I'm going to use bubbles. And let's see. Well, we'll just use bubbles like that. That's not really what I wanted. All right. I wanted to start with a blank slate like this here. I'm not exactly sure why it did. Oh, I know why. So make sure you don't have any of the data highlighted. Make sure your cursor is in a blank cell, not close to data, so that when you do an insert, it won't automatically go try to pick up data. All right, so we're just going to do bubbles. It's blank. It doesn't know what to pull in. All right, so we're going to tell it what to pull in. I'm going to go up here and select data. And unfortunately, again, there's no easy way to do this. We're going to have to add these in one by one. So I'm going to add my first one, series name. My series name is going to be brand. Or if you just want, you could just put, this in. Or you could, if you want to do brand A, you could type that in, brand. Here, let me show you. You could type in brand and then click on this, and it'll add the two together, brand plus whatever's in that cell, which is A. But I'm just going to stick with A for right now, or I'm sorry, this cell reference. And then X, what's my X for A is this one, and then for my Y, it's this one. Let's try that again. For my Y, it's this one, and then for my bubble size, it's this market share. All right, and I hit OK, and it plots it. And now I have to do that, and I'll show you one more. So what's my series name? Brand B. What's my X? X there. And what's my Y? My Y is here. And then what's my bubble size? It's going to be the share of the market, and hit OK. All right, so I'm going to pause this real quick, and then I'll come back after I've done each one of these and show you what it looks like. All right, so I finished adding all 4 brands. and you can see them here. So I'm going to close this out and just beautify this a little bit. And here we're going to do our data labels, and we want our series name here. Luckily here, because we added the series name when we did it, we can select series name up here. And I'm going to say put it in the center since I have a bubble. I'm going to bold it, and then let's do the next one. And let's do the next one. And let's do the next one. And then hopefully, let's see, sometimes it will allow you to do all of them together, but it's not allowing me. So I'll just do each one of these real quick. Right mouse click, format. Uh-oh, I don't want to format the axis. I want to format my data label. We want series name, get rid of the X value, put it in the center. And then one last one, this one right here. We're going to do the same thing. Format data labels. We want series name, get rid of the Y, put it in the center. All right, so there you have it. And I would probably format these ranges a little bit better, get rid of these grid lines, so we can do that really quickly, just so it looks more like a perceptual map. No grid lines there, no grid lines there. So now we only have our XY, and like I said, I would probably clean up my axes, and this is -2 to 2. And then I would also do my other axes. This -2 to 2 as well. All right. And you can see that, wow, this doesn't really give us much because these are right on top of each other. So if we wanted to magnify this a little bit more, we would change our axes again and just make our axes smaller, which is what Excel did for us to begin with. So, all of these numbers are below 0.5. So I might say -0.5 to 0.5 here, and then let's do the same thing on this one, -0.5, and make this one 0.5 as well. All right, so that looks a little bit better in terms of us being able to actually see what's going on. And then in this one, our market sizes are relatively the same, so you don't see much difference in terms of the bubbles here. But that's how you would do it. So there you have it in terms of how to do a MDS, or a multi-dimensional scaling analysis. Some last considerations for the multi-dimensional scaling analytical procedure. For one, there's no a priori considerations such as the number of centroids. Remember, this is going to just create data that you can put on a perceptual map. It is a simple representation of spatial comparison. So don't over-represent the results. Make sure you do some follow-up analysis so that you can make sure what you're interpreting for the results of the MDS are in fact what the MDS is telling you. Again, my name is Eric Riney from Webster University. You can contact me at my email information. You can also contact me on Twitter or LinkedIn, and certainly you can find me on YouTube. Join me for another one of my marketing analytics videos. There are more to come, and if you like this one, hit the like button, and you can also join my page. Take care, and I'll see you soon.